This video is a set of worked examples for rational equations and their applications. Let's start with proportion problems. Proportion problems are problems that can be created by equating two ratios. And the two ratios are often categorized so that one ratio is, say, for one instance, or case 1, and the other ratio has another commonality of another instance for, say, case 2. The numerators will relate in the same way the denominators relate. So let's see if we can use that sort of approach in the following problem. So if you want to estimate the number of wild horses in California, you can't possibly catch them all. So what a forest ranger does is he says, oh, here's all the wild horses. I'm going to catch 616 of them and tag them. So the ones inside this little circle are tagged now. And then he releases them. And so they're equally mixing. And after a period of time, in case 2, there's 244 horses are caught. And out of those 244 horses, 49 of them are tagged. So that's like saying, well, let's just take a slice out of our whole amount of horses. The tagged amount is going to be 49, whereas this total slice was 244. So assuming the horses mix freely, we want to find out approximately how many wild horses are there in California in total. Like, what's this big chunk? Because obviously that's impossible to catch them all. So we can set up two ratios into a proportion, and we can compare. We can say, well, okay, but how about the numerator represents those that are tagged, and the denominator represents those that are wild, total. And in case 1, instance 1, we don't know how many are total, but we do know that we've tagged 616 of them. So 616 of them out of a total of an unknown amount will be in the same proportion as the total of 244 horses where 49 were caught. And so you can let X equal the total wild horses in California, and you can solve your proportion. Now, because we just have two fractions equal to each other, it's relatively simple to solve. You can actually cross multiply and divide here. If you really wanted to be technical, you could multiply both sides by X, leaving you with 616 equals 49 over 244X. And then you need to take 616, multiply it by the 244 to eliminate the denominator, and then divide by the 49 to get rid of what's by the X. So essentially you're doing 616 times 244 and then divided by 49. And you could see that also as cross multiply and divide by what's left. So 616 times 244 and then divided by 49 gives us 3067.4. So approximately there should be about 3067 wild horses in California, according to the proportion given the data we've been presented. Let's try another proportion problem. So here we have a diagram of a tennis player hitting a ball, and so we've got some measurements here, and we have a property that if two triangles are similar, then their sides will be proportional. So this side to this side will be in the same proportion as this side to this side, as long as these angles are all the same. Like the triangle is essentially just an expansion of what it was. So think of when you go to zoom in on something, or you blow something up to make a big picture. That idea means the images are similar. So if images are similar, then we can use proportions. So in this case, I actually advise to draw the triangle out so you don't miss any numbers. So this smaller triangle here has 6 for its base and 0.9 as its height. Now if this is our bigger triangle, the second one, this bottom here is actually 12 and 6, so make sure you don't use the 12, you actually make it an 18. And then the height we don't know. So now we can make a proportion saying, for example, 6 is to 18, just like 0.9 is to h. This could be made in other ways, such as 6 is to 0.9, just like 18 is to h, or 18 is to 6, just like h is to 0.9. So this goes on. You have many possibilities, but they're all going to give you 18 times 0.9 divided by 6, which gives us 18 times 0.9 divided by 6, 2.7. So we've got 2.7 meters as the measurement here. Let's go on to motion problems. Now, motion problems, you may have seen these before. They involve rate, time, and distance. And we know that if we take rate, like miles per hour, times the time, like hours, you get the distance, the miles. And if you think about that, you go on the highway, say 50 miles an hour for 2 hours, you've gone 100 miles. So it's really nice to use these tables which show you the categories, and it just sort of organizes your data a little bit. So let's try that here. So we've got a car and we've got a bus. So let's put that down, car and bus, and we have rate times time equals distance. So let's fill in what we know so far. We know the speed of the car, which is the rate, is 5 miles per hour faster than the speed of the bus. So if the bus's rate is x, then the car is x plus 5. The car travels 220 miles. So let's just jot that down. Car travels 220 miles in the same time, so the times are equivalent, that it takes the bus to travel 200 miles. And they want the speed of the car and the speed of the bus, which we've already said, let x be speed of bus. And in this problem, it's in miles per hour. Now, there's a little difference here because we're not relating the distances like in other problems that you may have seen, but we're actually relating the times. So we don't have anything in here for time, but we can recall that if rate times time is distance, and we need to find the time, well, let's solve it for t. To solve it for t, you divide by r, and you get distance divided by rate. So if we take our distance divided by our rate, 220 over x plus 5, we get our time, and 200 over x will be our time. And we know that the times are the same, so now we have an equation which involves rational expressions. And since we've dealt with solving those, we can now solve this. So because it's just two fractions equivalent to each other, we can use the cross multiplication property. But if you're unsure of that, you can see that really you can use some algebra and make sure that the denominators are the same. So actually it's like we're multiplying by the lowest common denominator, which is x and x plus 5. So if we do that, you'll notice that we're left with 220x equals 200 times x plus 5, which essentially was a cross multiplication. And now we solve that, Subtract the 200, you have 20x equals 1,000. Divide by 20, and you get 550. So what does that tell us? Well, that tells us that the bus is 50 miles per hour. So you can say that the bus's speed is 50 miles per hour, but the car is going 5 miles per hour faster, which is 55 miles per hour. Let's try another one. So what's our component here? We've got a plane that travels against the wind. In the same time, so rate times time equals distance. Because it's at the same time, we can equal the times that it takes to travel with the wind. So 100 miles distance against the wind, 120 miles distance with the wind, and they tell us the speed of the wind, and they want the rate of the plane in still air. Now remember, you take the plane in still air and you would either add or subtract the wind. Always start with the still air speed because that's the predominant speed. We're assuming your plane does not go in the air if it cannot beat the wind. So what do we have here? We've got the plane in still air is Rx. So we've got x against the wind, so it's slowing it down by 20 miles per hour. With the wind, it's speeding it up by 20 miles per hour. Now again, we know that time is distance divided by rate. So the time here is 100 over x minus 20, and the time here is 120 over x plus 20. And since the times are equal, we can equal them into an equation. 100 over x minus 20 equals 120 over x plus 20. Notice that both examples here I've provided have equivalent times, but you could have had the same problem with a statement that says not the same time, but a total time. And so then you would say this plus this equals whatever the total time is. But that's not the case here. So again, we can cross multiply to solve. So we've got 120 times x minus 20 equals 100 times x plus 20. That gives us 120x minus 2400 equals 100x plus 2000. Subtract the 100, you get 20x. Add the 2400, you'll get 4400. Divide by 20, and you get 220. And what does that mean? Well, because you have a table, it tells you what your x is. Your x is your predominant speed, the speed without air, wind factors. So you've got 220 miles per hour as the rate of the plane in still air. You could also have work problems. Now, work problems involve completing a task. So let's just talk about this a little bit. Say you were painting a wall. Maybe you can paint the wall in 2 hours. Well, if you work for 2 hours to complete one whole job, what would your rate of work have to be? Well, the rate of work would have to be 1/2, because in 1 unit of time, you have completed half the job. So the rate of work is how much you've completed in 1 unit of time, and it's often the reciprocal of the time it takes to complete the whole component. the time you work for, and then the part of the job that's completed is determined by that rate of work. So you have rate of work times the time you work to get the job completed. So if you only work for 1 hour, you'll have 1/2 times 1, which is half the job because you've only completed it, half of it. So this is an important equation to think about. And really, I mean, it's essentially the same as rate times time equals distance, except instead of distance, we have the part of the job that's completed. So let's look at this problem here. We've got some info. David can paint the house in 12 hours. So what's his rate of work? Well, it'd be 1/12. Every hour he does 1/12 of the house. Now Bill can paint the same house in 9 hours. So what's his rate of work? 1/9. Now, sometimes we don't know the time, sometimes we do. How long would it take them to paint the house together? Well, what does that imply? Not distance, part of job. What does that imply? Well, we want David's part of job plus Bill's part of job to equal 1. And they're working together, so that means they're working together the whole time. So that implies that their times are the same. But we don't know them, so let's call them t, or x. So let t be the time that they take to do the job together. So then if you multiply, that's t over 12 is David's portion, and t over 9 is Bill's portion. So t over 12 plus t over 9 will give us 1, gives us the equation. And now, just as we solve, we can multiply through by the lowest common denominator, which in this case would be 36. So we multiply everything by 36, and we get 3 and 4. So 3t plus 4t is equal to 36, giving us 7t is 36. And so when we divide 36 by 7, we get 5.14. So 5.14 would be the number of hours that it would take. If you really want to convert this to minutes, remember it's just taking that ending of 60, so 0.14 times 60 gives you 8.4 minutes. So you could say 5 hours and approximately 8 minutes. Let's try another work problem. Here we have a tank that can be filled in 9 hours and drained in 11 hours. The question is, how long will it take to fill the tank if the drain is left open? So there are two forces here. It's like there's two people working. There's the filler and there's the drainer. The filler, the rate of work is 1/9. In 1 hour, it would complete 1/9 of the tank. The drainer completes 1/11 of its job, but its job is to minus the water away. So, and then we have our time and our part of job completed. Again, they're working together. So some problems will tell you, oh, the drain was open for, it was filling for 3 hours. How long would the other one work? And then you would put x. But in this case, it's working together. So let's say they're both x or both t. So that's x over 9 and negative x over 11. And together, you want it to complete one whole tank. So that's x over 9 minus x over 11 equals 1. Again, we can multiply through by the lowest common denominator. And we get 11x minus 9x equals 99, which gives us 2x equals 99, which gives us 99 divided by 2, which is 49.5, hours. So look at that. The tank could be filled in 9 hours, but if somebody forgets to put the drain stopper in, it would take 49.5 hours.